Good morning. Welcome to this webinar on hydrogen hosted by the Cleantech team at IP Group, today represented by me, Jamie Vollbracht, and Robert Trezona. If you don't know either of us, we've been working in Cleantech for all the technologies needed for the transition to net zero since the early 2000s. Over the last 10 years, we have built IP Group's Cleantech practice, where we have delivered strong returns, investing in deep technology opportunities. Hydrogen and its related technologies such as fuel cells and electrolyzers has always been part of our work and has risen to prominence recently, but its potential continues to divide opinion. Goldman Sachs believes clean hydrogen could help to decarbonise nearly half of anthropogenic emissions, estimating a €10 trillion addressable market by 2050. On the other hand, there are folks like Elon Musk who call hydrogen fuel cells fool cells. Who's right? Our view is that there is certainly a place for hydrogen in the transition to net zero, but the role will be nuanced, hence the title of this webinar, in which we hope to explore the question further. We are delighted to be joined by three distinguished speakers today: Professor Nigel Brandon, Dean of the Faculty of Engineering at Imperial College, Tom Mason, CEO of our portfolio company Bramble Energy, and Mark Selby, CTO of one of our alumni, Ceres Power. In the interest of time, I trust you and they won't mind if I don't provide exhaustive bios for each of them. Needless to say, they all have a wealth of relevant experience to share on this topic. The structure of today's session is as follows. First, Rob will give an overview of the hydrogen sector, drawing heavily on the work of the ETC, for which he is a commissioner. Next, Nigel will talk about the application of hydrogen for energy storage. Tom will then talk about hydrogen fuel cells and transport applications. And finally, Mark will talk about hydrogen production, focusing on solid oxide electrolyzers and the use of waste heat. We'll then have a Q&A. For that, please write any questions into the chat box and we'll do our best to cover as many of them as possible in the hour. Without further ado, I'd like to hand over to Rob.
Thanks, Jamie. So I'm going to be presenting work, as Jamie said, from the Energy Transitions Commission. For those of you unfamiliar with the ETC, it's a sort of multi-entity group bringing together finance, the energy industry, civil society, and energy producers. And really the objective for the ETC is to kind of provide roadmaps to net zero. How does a productive economy by 2050 or mid-century with net zero carbon emissions actually look? And one of the key things is not to be perceived to be captured by any particular agenda. So we're not for or against nuclear, for or against hydrogen, biofuels. The objective is to provide sort of balanced views on these critical topics as we transition to a net zero future. As Jamie said, alongside my role at IP Group, I'm a commissioner of the commission. And that means that we contribute a lot to the work, particularly this hydrogen work we've been heavily involved in. I'm going to go through some of the slides from this report. The report is available on the ETC website and has a lot of detail. It's been a product of 18 months of work. And we're going to share all these slides afterwards, so don't worry too much about the level of detail. So today I'm just going to talk you through some of the high-level conclusions and then hand on to Nigel. So one question I think people have been often asking is, 3-4 years ago, hydrogen was regarded as sort of a fringe topic in clean energy, and it's suddenly become central. And the reason for that is the commitment to net zero. So when people were talking sort of circa Paris 2015, around 80% emission reductions, a lot of industries, for example, aviation, all kind of assumed they would be in the residual 20%. As soon as you then say we're trying to keep global temperatures to as close to 1.5 degrees as possible, it becomes pretty clear you have to go to net zero by mid-century. And there are a number of sectors where you just cannot decarbonize using clean electricity from renewables. You've got to use something that effectively replaces fossil fuel molecules that we've been using for the last century. And that's why hydrogen is there. So hydrogen is now a thing because of the commitment to net zero. And this chart shows a scenario, if you look at the middle there, 2050 energy use, where the single largest sort of energy vector is renewable power, but hydrogen there in the dark blue is a very large part of the future sort of energy economy. So then in terms of sectors, there are sort of 3 or 4 really key sectors where there is no plausible alternative to hydrogen if you really want to decarbonize. And those are steel, ammonia, methanol, shipping, and probably aviation. So this chart, again, is a detailed chart, and we can share this with you afterwards, kind of shows the scale of hydrogen use in those sectors and the level of confidence that we have. So in the case of steel, we currently use large amounts of coking coal to produce primary steel, and it doesn't look possible to practically capture the CO2 from that process. So steel, for example, we decarbonized most cost effectively by using hydrogen directly to chemically reduce the iron ore. And so those 4 sectors are large. They are sort of gigatons of emissions today. And the reason hydrogen is now sort of interesting in other areas is if you were to decarbonize those 4 sectors with hydrogen, you generate a hydrogen economy of sufficient scale that the costs come down and hydrogen becomes attractive in other sectors as well. So this is the sort of, these charts show a scenario which really illustrates the scale of the change that we're talking about. And this really is why people are so excited about hydrogen. So we've had great success in the last sort of 20 years with solar and wind as new energy vectors, and hydrogen is really a new player. So we produce about 60 million tons of hydrogen today, but it's primarily produced and used in the same site. So on that left chart there, bottom left, grey hydrogen made from natural gas used in refining and say ammonia production is relatively large part of kind of global energy. But a plausible scenario for some net zero with the use of hydrogen sees that 60 megatons increase to over 800 in the ETC scenarios. So it's a massive change, and this industry, if we are to achieve net zero, will become very, very large. And this scenario, which is one of several scenarios the ETC have generated, shows the demand side where large users like shipping, aviation, cement, iron and steel all make use of that hydrogen production. In terms of the next decade, this chart sort of shows the different sectors that could use hydrogen, and they're color coded with respect to the sort of readiness. So, is there something commercially possible, and over what timescale? And you can see, for example, that a really important sector like steel starts off at pilot level today, but takes an awful long time to become fully commercial, just because of the scale of production involved and the great cost pressures on commodity steel production. However, there are other sectors that are coming into scope in this decade. And a good example is what I call logistics. So forklifts, delivery vehicles, which you'll hear more about in the future. Small electric vehicles, we need high uptime. An example of that is Amazon using hydrogen fuel cells in its warehouses today. So this kind of illustrates there are some sort of early adopter markets in the 20s that can pull through hydrogen demand. I've also put on there light duty vehicles, which is an area, as Jamie referred to, of some controversy. There's a lot of sort of public policy support behind them, particularly in Japan and South Korea, but there are those who think that advances in batteries will make them uneconomic. So this chart shows production costs of hydrogen. So the ETC has been working with Bloomberg on getting together data, looking at expected reductions in electrolyzer capex, so how you make hydrogen, or blue hydrogen, making hydrogen from natural gas and capturing it, plus future forecasts of both natural gas input for blue hydrogen and electrolyzer input in terms of renewable power. And really the takeaway from this chart is that if you look at the red line, so favourable locations like Chile and Australia could see very low costs of hydrogen. And these numbers have moved quite rapidly in the last 6 months. So people were talking about $5 a kilo probably only a year ago, and now there are forecasts well below $2. And at $2 per kilo and less, a lot of the other sectors beyond the sort of steel, ammonia, etc., start to look more interesting. So this is a very, very bullish forecast for hydrogen costs. It really says that the ETC sort of compound view is that green hydrogen made with renewable power and electrolysis will be the most competitive route. And a big part of that is our expectation that the the cost of renewable power will continue to fall right through to 2050. A really important consideration around this, which sounds obvious but is often sort of neglected in some of these comparisons, is the actual carbon intensity of the hydrogen production. And this is another reason why we think that green will ultimately be a bigger part of the future than blue hydrogen. So if you look at this chart here, those top 3 routes are just making hydrogen directly from natural gas with no carbon capture. That's grey hydrogen. So you're doing about 10 kilos of CO2 per kilo of hydrogen. Various options for blue hydrogen in the middle there, and the best we think is ATR with about 98% carbon capture. That's still about 0.8 kilos of CO2 per kilo of hydrogen. And then finally, the green routes from different renewables look most competitive on carbon intensity. And a really important consideration comparing these two is fugitive emissions upstream from methane production, which we think are very important. So in terms of cost, how do we get to that $2 a kilo? Analysis we've done suggests that we need something like 50 gigawatts of installed capacity to achieve that. And so this is something that's very much in the minds of policymakers as we go up to COP26. Both the EU and China, and actually now more recently the US, all unveiling ambitious plans around deployment of capacity, particularly electrolyzers. So that 50 gigawatt target is, we think, roughly where you're going to need to get low enough costs. And then in terms of the sort of investment opportunity, this is again another scenario showing for that overall economy, so ramping hydrogen production from 60 to 800 megatons by mid-century, what does the actual investment requirement look like? So the cumulative integrating onto that chart is about 15 trillion US dollars, and it will peak at around 800 billion per year. Now, if this happens, this is clearly a huge sort of new asset class, new type of infrastructure. And again, looping back to the beginning, that's why people are so excited about hydrogen as a sort of new player on the scene. So really the takeaways are that hydrogen has become important now because of net zero. Not every application, as Jamie said at the beginning, is going to scale. And we think people underestimate quite how cheap both renewable power and batteries will become. We're long as the ETC view, and I think also with an IP group, on green hydrogen, although there's clearly a role for blue. Green costs are surprising me, they're coming down faster than I expected. There's going to be a huge investment requirement, and really this is new plant. So a lot of the electrolyzer production is greenfield. And then really some thoughts on early sectors. Ammonia. So ammonia today is desperately important for fertilizer, huge quantity of greenhouse gas emissions. That is low-hanging fruit for hydrogen substitution. Also injection into refining, logistics, potentially grid gas blending, and light-duty vehicles in Asia. So thanks for that. And with that, I'm going to hand over to Nigel, who'll talk about the role of hydrogen in energy storage.
Thanks, Rob. I just checked, Rob, I've switched my video and everything on okay, right? You can see and hear me. Yeah. Okay, so if you can move on, that'd be grand. So Rob, thanks very much. So I guess I'm giving this talk slightly wearing 2 hats. Firstly, I'm wearing a hat as one of the founders of an energy storage company called RFC Power, and I shall talk a little bit about the technology and the approach that we're taking with RFC Power, very much addressing the longer term energy storage market. I'm also giving this talk, I think, wearing my hat as head of the UK's hydrogen and fuel cell research programme, and happy to take broader questions around hydrogen in Q&A as appropriate. So next slide, please. So, thanks, Rob. Great. So I'm grateful to my colleague Grant Wilson at the University of Birmingham. Grant and his team produced these very helpful flow pictures which show the flow of energy through the UK energy system. Obviously, this is a UK specific comment, but it applies to other places as well. And I just want to talk about this because it sort of brings into sharp relief some of the challenges and some of the requirements for technologies that deliver flexibility into the energy system, of which energy storage is one important example. The red line at the bottom of that. So firstly, what does the plot show? It shows gigawatt hours per day on the vertical axis over time. Interesting to see the some of the impacts of COVID and lockdown in the UK on transport fuel demand, for example, which is that central grey line. The red line at the bottom is the flow of electricity through the UK energy system, which is actually the smallest flow of energy that we have through the system. It's, however, a very important opportunity for decarbonisation, and then to use low carbon electrons to decarbonise other parts of the economy. And those little squiggles on that red line really do matter, because for electricity systems, you need to balance supply and demand second by second, minute by minute, hour by hour, day by day, and so on. If we look at the grey line across the centre, that's the flow of energy as transport fuels, so primarily fossil fuels in the form of diesel and gasoline. As I say, note the fall in demand as lockdown hit. But broadly speaking, it's subject to a global pandemic. Outside of that, it's a pretty flat profile. And obviously, one of the areas of interest is to shift that into electricity, and Rob talked a bit about that, either in the form of being carried directly as electrons in a battery, or carried as a molecule in the form of hydrogen. Now, an electric car, whether it be a fuel cell or battery electric car, is more efficient than an internal combustion engine car, sometimes somewhere between 2 and 4, depending on how you've chosen to do it. But it will require clearly an increase in electricity generation of somewhere from around 800 gigawatt hours per day to somewhere between 12 and 1600 gigawatt hours per day. And we would want to do that with renewables. Now, the other line on there, which is the blue line, the big blue line, that is the flow of energy as natural gas. And I think this is, to some extent, the biggest challenge of all, because of the seasonal variation in our natural gas demand in the UK. Of course, we use natural gas for heating, both for industrial heating and space heating, as well as to some extent for power generation. And it's this big seasonal variability that creates a significant challenge, and the need for some longer term, the reflections on some need for longer term storage. Obviously, for heat demand, we can think about shifting that natural gas heat demand into electricity. For example, we might choose to do that with heat pumps. Heat pumps are something like 3 to 4 times more efficient than heating with natural gas in the summer, and probably about 2.5 to 3 times more efficient in the winter. But you can see the peak demands there going up to something like 4,000 gigawatt hours. And if we're going to meet that peak demand all with electrical heating, even with a heat pump, say, of coefficient of 4, which is we would never achieve in the winter, that's still an extra 1,000 gigawatt hours peak electricity generation. So there's an interest in meeting some of that energy demand with hydrogen, perhaps, as well as with electricity. But it's also, how do you balance the system across these different timescales, particularly with looking at some of these big seasonal variations. Next slide, please. So this is some work my colleague has done at Imperial College, Professor Goran Strabak, and he's looked at the impact of increasing wind penetration into the UK electricity system. We will rely extensively on wind for our renewable sources in the UK. And there are 2 plots on here to take away. Firstly, the right-hand side there says, if you increase the amount of wind on the system, as you increase it, unless you do something about the ability to balance the system better, you will need to increasingly curtail that wind at times of peak wind generation and minimum demand. And that becomes an expensive investment in wind generation. Or you need to invest in the infrastructure to allow those peak loads to flow through the system. But then you end up with a decreasing use of that infrastructure, and therefore a more expensive infrastructure being used less of the time, with the associated on costs. And his work suggests a market in the UK alone for flexible technologies, so that would include storage, but not only storage, in a post-2030 UK scenario of greater than £8 billion a year, and that grows over time as we move closer to a net zero system. Next slide, please. The other feature of this, in particular looking at increasing reliance on wind for our electricity generation, is that it's well known that in Northern Europe, we get a low in the winter in terms of wind generation. And how you choose to balance and mitigate that is a really important question. This again is some work from Goran's group, and it looks at the impact of the number of weeks with low wind against if you were to balance that entirely with hydrogen, how much hydrogen would you need to store? And if we look at the 1 week case there, let's look at the limit. You can see that it needs about 10 terawatt hours of storage. Now, just to put that into perspective, I don't know how many of people listening on the call have ever been to the De Norwig pumped hydro station, so-called Electric Mountain in Snowdonia, purpose-built, large-scale pumped hydro facility in which 1 million cubic meter cavern was excavated inside a mountain. That provides 9.1 gigawatt hours of storage. So we would need 1,000 of those to deliver the 10 terawatt hour energy storage just for 1 week. And clearly, I think that demonstrates the challenge. There has been a really good German study looking at the capacity for underground storage of hydrogen, in which you would use solution lined salt caverns, which are a lot easier and lower cost to manufacture and produce. And they estimate that the UK onshore and nearshore hydrogen storage capacity is 2,000 terawatt hours, so far more than we would need to deliver this sort of storage. So that's an interesting question there, and an opportunity for hydrogen in longer term storage. Next slide, please. And if we come down a bit in terms of our storage duration, and we start to think about not looking at weeks of storage, but hours of storage, this is a study from the Californian Energy Storage Alliance, looking at the 2045 situation in California, which is predicated on the Californian target of 100% zero emission power generation in California by 2045. And they say that it's very clear that what they given that that would rely extensively on photovoltaic power, this would need to be met by a 10-hour energy storage system. So again, it's a longer term energy storage system than we currently need, which is often more in the scale of minutes to an hour or two. Next slide, please. So this is why, this is from Bloomberg New Energy Finance. There's a lot of forecasts here which talk about the increase in the market for longer term storage, somewhere north of 4 hours. For example, these 10-hour backup storage systems for diurnal backing up of solar, or even into the longer term, more strategic weeks of storage to manage intermittent shutdowns in wind supply in the winter, for example. Okay, next slide. So RFC Power is a company that's playing in this space. I'm not going to tell you a lot about it, but happy to follow up with questions or to pick up subsequently. RFC Power are developing a new type of flow battery. So flow batteries are a technology well suited to multiple hours of energy storage. Effectively, they produce, in a flow battery, it has a device that's not dissimilar to a fuel cell or an electrolyzer at its heart, and it produces a redox couple, that is an oxidized form of a chemical species and a reduced form of a chemical species that it stores in tanks. And if you need more energy, you need a bigger tank, and tanks scale quite cost effectively. So as the technology, as you need more and more hours of storage, this is a good way to go. And what we've developed with RFC Power is a new chemistry. It uses a hydrogen manganese, so-called hybrid flow battery. We don't use vanadium, which is the most commonly used species in flow batteries, both because vanadium is expensive and because most of the vanadium comes from either China or Russia, so there is a supply chain concern. Instead, we use manganese using a patented chemistry. Manganese is the fourth most used metal after iron, aluminium, and copper. It's widely available and globally sourced and low cost. And indeed, the electrolyte is only about 1/10 the price of a vanadium system. This gives us a battery that has long lifetime. Thousands of hours have been demonstrated for flow batteries. Deep discharge, we can generate from 100 to 0% state of charge. A round trip efficiency, so we get about 80%, so we get about 80% of the energy out that we put in. Much safer than the lithium ion battery, and a low cost, overall cost of storage. Next slide, please. Okay, thanks. So it is also one that uses hydrogen, so it can loop into the hydrogen system. And one of the ways of thinking about this is if you want to make hydrogen, and then in an electrolyzer, which is for low temperature electrolysis about 65% efficient, for high temperature electrolysis about 90% efficient, and then convert it back to power in a fuel cell, which is perhaps about 60% efficient. Overall round trip efficiency is about 50% at best. If what you want to do is store energy, then you can instead use a technology like this, which gives you an 80% round trip efficiency. Of course, that's not to say it's the same as a fuel cell and an electrolyzer, but if the function of the device is energy storage, it's a far more efficient way to do it. Where are we today? Well, we've demonstrated 700 cycles. This is the left-hand chart. I won't dwell on this because I'm over time. And we certainly predict, and this is based on our quite detailed cost model, the chart on the right there shows that as the storage duration goes up, this technology becomes significantly cheaper than lithium ion, depending on one's price assumptions for lithium ion, of course. But once you're up at about 8 hours, you're under $100 a kilowatt hour. And if you choose to go up to 24 hours, you're down at about $50 a kilowatt hour. Next slide, please. So this is RFC Power. Happy to take questions on it. It's addressing this very large emergent market in longer term energy storage. It does interface with the hydrogen economy as well, which offers additional benefits. We have a very broad and well protected IP set, and happy to talk about the business model as well. But Rob, I'll stop there because I'm over time. Thanks.
Thanks, Nigel.
Hey everyone, thanks Nigel. So my name's Tom Mason. I'm going to give you some thoughts today on the use of hydrogen in mobility and a little bit on Bramble at the end. So some context of fuel cells in this case. So we have to think about decoupling power from energy here. So fuel cell is an engine. It's the way of turning that fuel into something useful, electricity in this case. Whereas hydrogen, of course, is how you store the amount of energy, how far your thing can run, how long it can run for. And often, if we think about mobility applications, kind of the reason you go for hydrogen and fuel cell systems is for two reasons. The first is weight, and the second is uptime. So at the bottom of this slide, we have a couple of bits of context in terms of how a fuel cell system compares to a battery system. So in terms of gravimetric energy density, so that's the amount the overall system weighs per mile of range added. You can the numbers here. The battery system comes from a Tesla, so about 1.75 kilos of powertrain weight per mile of range. Whereas a fuel cell system, so the fuel cell system here is modelled on the Toyota Mirai, which is a fuel cell vehicle from Toyota, is about 0.4 kilograms per mile of range. You can see there's a very significant difference in terms of the amount of weight. And so if you're in a logistics scenario where you care about the amount of load you can carry and the total mass of the thing you're trying to move, and this is where fuel cell systems have a significant advantage. And the flip side to that, of course, is the refuel and recharge time. So we're comparing here ultra rapid chargers, so sort of 150 kilowatts and above, and can add at 500 miles of range per hour of charge time. And so which is perfectly good enough for personal travel for a lot of people. But especially when we move into logistics scenarios where uptime is very important, and being able to sweat those assets, it starts to become more limited. Whereas a fuel cell system has a much more typical user experience from petrol and diesel. So you can add kilos of hydrogen in a few minutes. So the Mirai, as an example, is about 4 kilos of hydrogen. You can do that in 5 minutes. And that gives you about 300 miles of range. So you end up with a comparison of 6,000 miles of range added per hour of refueling, which compares to. So mobility, you have these three mantras: range, weight, and cost. So give an example here of light logistics. So recognizing what Rob said at the beginning about the uncertainty of where you use hydrogen. I think logistics is one of those scenarios where the uptime of that asset is very important, especially when you start considering the move towards next day retail and online shopping. So the examples given here is what Mercedes have been able to do with their Sprinter vehicle. So obviously very typically powered by diesel. They also produce one now which is powered by lithium ion. And you have a significant premium. You have a significantly lowered range from several hundred miles of diesel and fast fill-ups down to 95 miles of range. Obviously changes seasonally, but you also significantly reduce the load capacity. So again, this is where you can compare fuel cells are favorable in all of those metrics. So amount of range, amount of load carrying capacity, and we'll come to cost in a bit. So refueling infrastructure is quite interesting. So the amount of fast chargers, I mean, there's the charging infrastructure in the UK is growing very, very quickly. But in terms of ultra rapid chargers, so those 150 kilowatts and above, they're still very limited. We have less than 1,000. And when you consider that there are about 250,000 pure EVs on the road in the UK, I don't think anybody would really argue that the amount of infrastructure we've got is enough. When you consider we have 30 million passenger vehicles on the road, starts to question whether the amount of deployment is anywhere near enough for ultra rapid charging. And when you compare that to the sort of infrastructure that will be required for forecourt hydrogen dispensing, actually at a national level, the cost would be lower to go to hydrogen. Now, that being said, I'm far from an advocate of everybody having a hydrogen vehicle, although I do drive a Mirai. Having a battery car can suit a lot of people, especially if you have off-grid parking, so you're able to charge up at home, subject to battery prices declining as everybody expects to. It's probably the lower total cost of ownership. But you know, in the UK, there are 9.5 million households that don't have off-street parking. And when you consider that they would all require some form of rapid charging, whether it's ultra rapid, of course, is debatable. But with hydrogen, it certainly offers a solution in that sense. So now I've got a couple of examples, one in aviation and one in marine, where it starts to put the challenge of electrification into perspective. So this is really, again, about the advantage of hydrogen being where moving a higher mass over a longer distance is where hydrogen systems win over batteries. And a couple of numbers here. So a 6-seater aircraft, so very, very small, requires about 500 kilowatts of load. So again, when you start to look at the mass of batteries, you are limited then to the tens of kilometers of range. So even in Europe, that's not really enough. When you start looking at much bigger aviation, so more typical, so 737 uses about 7 megawatts of power at cruise. And so if you were to build a battery that was able to store that amount of energy that would enable 1 hour of flight, so you know, London, Edinburgh, London, Paris, that sort of thing, or Amsterdam, you require about a 45-ton battery. And when the 737's gross takeoff weight is 56 tons, you can see that, you know, that's just not going to work. And so that's where we start to see hydrogen being a real potential for decarbonising that power. So marine is where it starts to get even bigger. And so you saw from the ETC report that Rob showed earlier, marine is a particular example where hydrogen has a strong use case. And so if we look at a container ship like the one in the picture of the Evergreen that got stuck in Suez, they require about 80 megawatts. So, you know, over 10 times the amount of energy required for aviation. And so from a typical trip from China to the UK, that would use about 60 million kilowatt hours of energy. So, you know, you also then have the refueling part of that, or recharging rather. And so you know, a typical container ship of that size takes 3 days to unload, and that will require a 1.6 gigawatt connection. So again, these numbers are massive. You know, it's more than 7.5 million UK homes, and you know, more than any of the individual nuclear power plants in the UK can produce. So again, puts into perspective. That's for a single ship. So it starts to put into perspective the challenge of decarbonising that. Also, you know, the asset life for marine is very, very long, and batteries are particularly challenged when it comes to decades-long asset lives. And so just to conclude, so what do fuel cells need to be? So they, you know, the fuel cell is the engine, as I said, for hydrogen. It needs to be scalable in manufacture. It needs to be cost effective, particularly over battery technology, but also internal combustion technologies. It needs to be durable, long life, and it needs to be easily integrated into form factors. And that's several of the advantages that Bramble Energy boasts in its PCBFC technology. And again, happy to answer more questions on that later. But thanks. I'll hand over to Mark.
Thanks, Tom. Yeah, so pretty broad range of topics. I guess everyone knows Ceres Power from the fuel cell domain, but I just wanted to give you a bit of a preview of some work we're going to publish later in the year about industrial hydrogen and our work on electrolyzer technology. So in the interest of time, I won't dwell on who we are, but safe to say that Ceres has grown very rapidly over the last few years, and that's really been enabled by a very clear understanding of what our technology does, very clear understanding of our business model, and the backing of some fantastic partners, people like Bosch, people like Weichai, people like Doosan, who've really committed to taking the technology forwards. And that's enabled us to take a step beyond fuel cells and start looking at the use of this technology for hydrogen production as well. So we talked a lot about energy storage, energy systems in general, and particularly in the fuel cell and the RFC power context. But I think one of the lesser understood parts of this story, or the less talked about parts of this story, is what Rob called the hard to abate sectors. So steel, ammonia, potentially synthetic fuels. Those 4 or 5 sectors on that ETC chart are really important. And I think I've heard Nigel say this a few times before, that the hydrogen is probably the second best solution to a vast range of our current decarbonisation problems. But there are 4 or 5 things where hydrogen is the only solution. And a lot of those tend to fall into what I might call the green chemicals sector. So reducing agents for steel, agrochem, petrochem, converting air captured CO2 into effectively net zero carbon or closed carbon cycle products like plastics. So hydrogen is going to be really important, but it's probably going to be really important in places that there is not a very rich debate about. And I think that's one of the things that came again out of Rob's chart. He had some analysis from Systemic showing confidence and contribution to total hydrogen market. And I think most people that are talking about hydrogen today would find that a bit surprising. So I'm just going to talk about some analysis where we're going to publish later in the year, particularly around this green chemicals space and integration with industrial heat sources. So here's the chart that I've adapted from a Royal Society paper from a year or so ago. And let's just start on the right and work back. So if we start to think about really important things in decarbonisation, ammonia is going to be important, whether that's ammonia in agricultural context, which today is worth a couple of % of primary energy, or whether you start to think about using it on ships, as Tom's just talked about in the marine sector. Hydrogen itself is going to be really important as a chemical, but then we're also talking about things like long-range aircraft fuels, so synthetic kerosene derived from air captured carbon, for example. And if you work back a couple of steps from the right hand side on this chart, one of the key things that goes into both of those processes is you start with hydrogen. Whether you're mixing hydrogen with nitrogen or you're mixing hydrogen with carbon dioxide, hydrogen is a really important stepping stone on that chemical journey to these what you might call energy dense, high energy density molecules for the energy system, or indeed for green chemicals like in steel production itself. So if you work back and you say, well, electrolysis is definitely going to be one of the technologies that is important in supplying that hydrogen, you've got a couple of routes. You always start with water, you always need electricity, and some technologies create the option for integrating with low carbon heat sources. And the question that I had when I first started looking at this is, well, is there a readily available supply of low carbon heat sources? Now, you can start to think about waste heat from industrial plants. Refineries release lots of steam, for example. What's less understood, I think, is processes like Haber-Bosch, where we produce ammonia, are often said to be very energy intensive, but the energy intensive step is actually to supply the hydrogen. So if you look at ammonia production as one example, something well over 90% of the energy that goes into that process is to supply the hydrogen, not supply the Haber-Bosch process itself. And actually, when you look at this in some detail, processes like Haber-Bosch for ammonia production, or Fischer-Tropsch for synthetic carbon-based fuels like e-kerosene or synthetic diesel, actually produce heat. So the available heat of an appropriate grade for electrolysis is going to scale as some of these synthetic green chemicals scale also. But the question is there an available source of heat today, or do you have the classic chicken and egg situation? And what you find when you look at this, and we took some, oh, sorry, before we move on, I think it's worth just talking about what flavors of electrolyzer there are. I think when people look at these massive installations of electrolyzers and they see the news flow from the Middle East, Saudi Aramco, those sorts of projects, these gigawatt scale projects, they're predominantly talking about alkaline technologies. And so that's a very, very mature technology. It's been around for well over 100 years. It works, it's super mature, and it's available at large scale. I mean, if you look at companies like Nel, you'll see pictures from their pre-war systems, and these electrolyzers are already at hundreds of megawatt scale. So they're available, they're mature, they're reasonably efficient. So I would call that the incumbent technology that every other technology has to think about beating. I would say today that the challenger technology is PEM electrolyzers. There are several people working on this. They've got some real advantages. They're pretty mature, they're less mature than alkaline, they're reasonably efficient. Their party trick is they can play tunes on the energy system, so they can turn up and turn down very rapidly, so they can provide grid services to the energy, and they're really great for matching with highly variable renewable energy sources. But where there's the potential for disruption is high temperature electrolysis, and that disruption comes from the fact that if you're running a chemical plant or a steel plant, you need high availability of your electrolyzer, so you're going to run it a lot of the times, or capacity factors, and you're probably going to be close to an existing grid system rather than a bespoke renewables installation. So you're going to pay a premium for your electricity, and your assets are already sunk. So efficiency and energy costs are what are ultimately going to dominate your hydrogen production. So is that efficiency premium enough? And is there a scale of market that makes sense to deploy high temperature electrolyzers? So I'm going to show you this graph in a few different forms, and I'm going to rescale this y-axis, which at the moment is waste heat, and these bins are temperatures of which energy is available in the form of steam. And this is from a paper from a couple of years ago that did a survey of waste heat availability in Europe, and it's in terawatt hours and it's in different grades. So the question is, if I had 100 terawatt hours of waste heat at between 100 and 200 degrees centigrade, what would I be able to couple it to in terms of electrolyzer capacity? And the same goes for these different temperature buckets. So if I just rescale the same data and look at it in terms of electrolyzer capacity, I'm already close to 40 gigawatts, even in that lowest grade heat. I get another 60 gigawatts between 200 and 500, and I get another 70 gigawatts nearly at 500 to 1000 degrees C. And just to make that, put that in context, the European green hydrogen target is around 40 gigawatts. Now, I'm not for 1 second going to make the claim that all of that waste heat is available in a practical or economic way, or that all of the green hydrogen target for Europe is going to come from high temperature electrolyzers. I'm not. My point is that there is a large available source of heat today at relevant temperatures available for the deployment of high temperature electrolyzers. And that's a really important step to growing a market. And the point I made a few minutes ago around Haber-Bosch and Fischer-Tropsch being exothermic around the process means that that high temperature heat, particularly that middle bucket, that 200 to 500 degrees C bucket, is going to scale dramatically as our dependence on those green chemicals increases. Now, I'm going to add one complication to this graph. We've talked about the efficiency of electrolyzers being a function of temperature. So on this green line, on this right-hand axis, the question is, well, if I've got heat at 200 to 500, what's the efficiency at which I can produce my hydrogen from an electrical point of view? I'm effectively counting my heat as free at this point because it's waste heat. So I can get, if I've got heat at around 200 to 500 degrees, I can achieve well over 85% efficiency. If I go even higher to 500 degrees, I can get well over 95% efficiency. So there are some really important opportunities to be taken in terms of low cost green hydrogen that maximizes the use of our resources. I think one of the things that's often neglected in the current debate or the current conversation about the journey towards net zero is not only do we need to get carbon out of the system, we also need to do things much more efficiently. We have to reduce our total consumption of primary and final energy in order to make the progress we need. And therefore, systems like high temperature electrolysis that provide these very high efficiencies are going to be extremely important. So what does that do? I mean, Rob put some numbers about glide paths for high temperature, for green hydrogen over the next decade or two. And if we take relatively conservative assumptions about energy cost and capex for these technologies, we can already see well within the next decade, certainly the second half of this decade, where with high temperature electrolysis, relatively low grade heat, but integrated in a thoughtful manner, that we can already get sub $1, $1.50 a kilo of hydrogen. And that's really important when we think about decarbonizing some of those really challenging sectors like steel or agrochem or petrochem for that matter. So high temperature thermally integrated electrolysis systems are going to be key technologies for the hard to abate sectors. They're going to be really fundamentally important for e-fuels. If you start to look at some of those processes that I've talked about, like Haber-Bosch and Fischer-Tropsch, the level of differentiation, if you have a high temperature electrolysis technology, is really quite staggering compared to the lower temperature PEM and alkaline. So that's likely to be a sweet spot. So if you believe in synthetic fuels, if you believe in green chemicals, you almost by definition, even if you hadn't realized it, have to believe in high temperature solid oxide electrolysis. And a key thing for us is, a key thing for the whole sector actually, is what's the rate at which these technologies can scale. So a key premise that Ceres is working on, and we're demonstrating this technically at the moment, is that the same technology that we've licensed to our partners like Bosch and Doosan and Weichai can be used as an electrolyzer technology. That's really important. So if you look at Bosch and Doosan today, they've committed to bringing on production of fuel cells of around about 1/4 gigawatt by 2024, around about. Now, there is a quirk of the thermodynamics that means that we get about double the power density in electrolyzer mode that we do in fuel cell mode. So already there is the option to produce roughly 0.5 gigawatt worth of electrolyzers by the middle of this decade. Now, you can imagine that the access to capacity doesn't scale linearly. When a technology is proven, when it goes, they tend to grow relatively fast. So it's relatively easy in my mind to imagine that by the end of this decade, that there'll be substantial manufacturing capacity in the many gigawatts for our steel cell technology, and that when partners choose to take additional licenses so that they can sell their technology as an electrolyzer, there is a real opportunity to deploy this technology extremely fast because of those current manufacturing investments of those great partners. And it's well matched with a market that exists with available industrial heat. So I'm going to leave it there. I went at a little bit of pace to try and catch back a bit of time. I hope that helped.
Thanks, Mark. That was super. Thank you, everyone, for such interesting presentations. We've got 6 minutes to run. So if I slightly run over, I'm going to have a crack at trying to cover some of the great questions that people have been sending in. Thank you very much for those. And I've had a crack at trying to pull it together. First, there seems to be quite a lot of interest in hydrogen storage, how hydrogen is going to be stored. And I wondered if perhaps Nigel first and then Tom, you could pick up on this and really just dig into, what do you think is going to be the predominant system that's going to be used for hydrogen storage, or do you see a mixture of different solutions?
Well, why didn't I let Tom speak about on-vehicle storage? And just in terms of non-on-vehicle storage, if for the kind of strategic long-term, 2 or 3 weeks buffering a global a national energy requirement, which comes into the terawatt hours range, I think the only really credible game is solution mine salt caverns. There's plenty of capacity around Europe. I'm not so familiar with the capacity elsewhere. Simply haven't looked. You store that at somewhere between 70 and 200 bar hydrogen. It's already done in the petrochemicals industry. So as a technology set, it's pretty well understood, and we store lots of natural gas that way as well. If you want to go, if you're looking at kind of backing up solar PV on solar farms and so on, then that's a different situation. If you want, 6, 8, 10, 12 hours of storage, I think at that point, then you're engineering overground compressed hydrogen storage. I don't think it's liquid hydrogen storage. The energy burden of liquid hydrogen is just too high, and the costs of running that equipment are too high. Certainly in the case of RFC power, where we're looking at sort of somewhere between 4 and 24 hours of storage, that's a relatively low pressure, a few bar to perhaps a few tens of bar max system.
Thanks, Nigel.
That's fine.
Tom,
Yeah.
can you pick up the sort of smaller scale vehicles?
Yeah, I think in most mobility applications, it's going to be compressed gas. And it's very, there's a very typical wide use standard at 700 bar, 350 bars also used. Again, it slightly depends on what you're sensitive to, whether it's space or weight. You can get a slightly higher energy density if you do a lower pressure, but of course it uses more space. So it sort of largely depends. There's a few other people doing things like LOHCs. There's some interesting things that some interesting things out there. Of course, you can use ammonia in some of these scenarios, so you can reform it back to hydrogen. I mean, it sort of largely depends on what you're. But I think in most mobility applications, particularly in vehicles, say whenever they're high, heavy to light, you're going to use compressed gas.
I think the one area maybe that's a bit different is shipping. You talk about ammonia and shipping.
Yeah,
it's not well understood, but it's absolutely clear that ammonia is directly a fuel for high temperature fuel cells in their own right. So you can convert ammonia on a high temperature solid oxide fuel cell at over 60% efficiency.
Yeah, absolutely.
Super, thanks all. So next I was going to do, having done a bit of how on storage, I was going to do a bit of where. And Rob, initially direct this question at you. A question that came in about making hydrogen in cheap places and then shipping it. Can you maybe talk to whether you think that's going to work out, or how you see sort of cost of shipping?
Yeah, thanks, Jamie. So we looked at this in quite some detail in the ETC. and partners like Ørsted and Snam, who kind of, Snam run pipelines, were very helpful. I guess for me anyway, the unexpected conclusion was that if you're moving large volumes, so more than about 10 tons a day, but into 100 tons a day of hydrogen, pipelines are actually quite cost effective. That's green new pipelines, so laying new pipelines to move hydrogen. That was unexpected to me. And when I say cost effective, for example, if you wanted to move, 500 tons per day of hydrogen across 1,000 kilometers, the additional cost of that hydrogen at the end, when you sort of look at the total cost of it, is about 10 cents per kilo. So we were talking earlier about $1 to $2 per kilo production cost. So it turns out to be quite a small cost. And all of this, though, is powered by large volumes. So at the moment, it's expensive to move hydrogen around, and a lot of it's moved in trucks. But pipeline infrastructure is actually attractive, and people are talking about moving hydrogen from, say, North Africa to Europe. Very long distances, more than about 5,000 kilometers. There is a case to convert hydrogen into ammonia and put it on ships. And the famous case of that is from, say, Australia to Japan. So you want to move hydrogen over that distance, then it's worth paying the energy penalty for that conversion. But yeah, it looks like pipelines are going to be important. Having said that, trucks are not necessarily prohibitively expensive. So you can move, both in compressed and actually also liquid hydrogen, say, hundreds of kilometers for order 50 cents per kilo. But all this stuff relies on the industry getting started. So today's costs are much higher than that. But once the industry is up and running, there are no fundamental barriers, really quite low transportation costs. And that's good news for countries and regions with good renewable energy. So windy countries, Norway, for example, actually the UK, but also the Middle East and Australia, it looks possible to move that energy as hydrogen relatively cost effectively.
Thanks, Rob. So as I'm going to run over, but only very slightly, just to cover two more questions. Next one, sort of continuing the where theme, is for you, Mark, and it's really around scale. So a couple of questions have come in around sort of what scale will this hydrogen production happen at? Is it going to be decentralized? In the state that we've seen some other clean energy technologies, or will only be very, very centralized large scale plant?
Yeah, I mean, I think when you look at the, I don't have the exact algebra, but I'll give you an order of magnitude. So when you start to look at the consumption of hydrogen in decent scale steelworks, you're into the hundreds of megawatts scale. So a decent industrial plant is going to be into the hundreds of megawatts to low gigawatts when you start to think about decarbonising it fully. So these technologies are going to be large. I think that the electrolyzers themselves are going to be modules, whether that's a 1 megawatt module or a 10 megawatt module doesn't really matter. So they're going to be deployed in arrays. And I think one of the key things that is favourable for the sector is that if you've got a sunk investment today in an ammonia plant, or even let's pick an example that's live. So most diesel today is processed with hydrogen as hydrogen desulfurization. You could start to replace that grey hydrogen day on day immediately with small scale electrolyzers at whatever scale you choose to deploy them. So there are markets where there is an opportunity where it's not a binary thing, where it scales very linearly and very incrementally and allows you to decarbonize those assets over time. And I think that's a really important enabler that has not happened in some of the other sectors, where you need to go from nothing to something very large in a single step to make it credible. Interestingly, that's not the case for the credibility of green hydrogen in the green chemical space today. Thanks, Mark.
A neat segue, weirdly, into the final question, which is around tipping points that's come in. So, and this is, I guess, a question for the whole panel, but perhaps one or two of you can put your hands up if you really want to answer it, or we can cover it all if you've all got lots to contribute. So it's really what are the tipping points that people will see for hydrogen to see this kind of huge growth potential, and when do you think we will see them?
Probably
nice easy one to start.
Yeah, so let's start.
Go for it, Rob.
So I think it's for me the big bottleneck is electrolyzer supply. So as of 2019, I think the global production of electrolyzers was 0.1 gigawatts, and that really is the constraint. So you talk to people wanting to do pilot projects in steel and ammonia today, their concern is getting access to the equipment, because up until all this stuff happened with net zero, this was a small industry. And so everyone's scrambling to gear up their supply chain, build factories and so on. So I think it's at the point where electrolyzer supply gets into the multi gigawatts. It goes from being, you know, relatively batch assembled cottage industry to large facilities producing, you know, large quantities of kit at good quality. And I think, you know, it's not a question of looking at the announcements, right? Because if you add up all the announcements, there's 100 gigawatts in the pipeline. It's the actual, you know, electrolyzers produced and installed in projects. I think when we get to run rate in the gigawatts, I think we'll have broken the back of it.
Thanks, Rob. Good answer. Anything to add, or is that enough?
No, I think there's an important policy point. At the moment, people don't yet value carbon emissions. Now, whether that's carbon tax or a carbon credit or something else, but I think as soon as there is serious carbon policy, and hopefully COP26 will show something a bit like the G7 that is global and significant in its nature towards climate change, then I think actually these things snowball pretty rapidly.
Nigel.
Yeah, just a comment really, which is that hydrogen is an integrated system. You need to produce it, you need to move it, you need to store it, and then you need to use it again. You know, so it's fine to focus on the generation side, but no one will build it as no one can move it, store it, and use it. So it's an integrated whole. So I think there's a tipping point here around looking at this, looking at that whole supply chain is really important. And I think that sometimes gets missed by the policymakers. They can't just create a generation side demand. You know, there has to be a demand side. So that's something else to bear in mind. But I completely agree with the point on manufacturing scale. I think this is a technology. Whatever they are, whether it's a fuel cell or an electrolyzer or a flow battery, they're all modular. They all like a lithium-ion battery. They lend themselves to vast, you know, high volume repeat element manufacturing. And obviously, Tom through Bramble has got another approach to that, which genuinely drives scale. But that they all lend themselves to those volume manufacturing. So it's a really important area for whichever technology you're talking about. Is manufacturing volume.
Thanks, Nigel. I'm going to wrap up there, Tom. Or have you got anything else you want to contribute? No, great. Okay. Well, so it's very slightly over 5 minutes, but hopefully that was useful for everyone to get an opportunity to answer the questions. Thank you, firstly, to all the presenters for their contributions, and indeed to everyone who joined. I think my conclusion is that actually the title of the session was pretty good. It sounds like hydrogen is a huge opportunity, but it's nuanced. Yeah, look forward to follow up with many of you. Thanks again.
Thank you.
Thanks, Jamie.